All right, welcome everybody. Welcome everybody on Zoom. Welcome everybody in the lecture hall. So today is the celebration of the end of the semester. It's literally Friday afternoon, so it's the last half day of lecture, and then hopefully you can take at least a few days of good rest, maybe a few weeks, and work on your exam. There will be no new material today. I'm not going to throw anything new at you. On the contrary, we'll just go through what we have been learning during the semester. We'll have a quiz game, you know, in the multiple choice style. And you can ask questions. I'll tell you a bit about the exam as well. And hopefully that will be a good end of the semester for you. I have to say in advance that because one of the TAs is sick, who should have done the exercise session, we had to find another solution, and the exercise session will be fully online after this lecture. However, if you want, one of you can put their laptop in here and project for those of you who want to stay in the room. So there are two options. Either you all go and connect yourself to Zoom for the exercise session, or one of you puts the laptop here and connects it, and you can just watch from the lecture hall, right? So it's really up to you. We can stay for a few minutes. Unfortunately, we have another meeting, so we cannot stay. But we'll help you configure the laptop if this is what you would like to do, right? I see a few nodding heads, so we'll do that. All right. For you on Zoom, it doesn't change anything. Just just connect as usual with the Zoom link to the online exercise session. All right, so, okay, let me just go through the slides. You will see it's nothing new. I'm just going to recap what we've been doing, and then you will see it's a lot of things. Yes? Yes, I will. So usually I do an exception for the first and last lecture, because I want you to just sit back and relax and enjoy, right? There is nothing new. I will upload the slides, but today you should just, take a step back and listen. There is nothing new. I mean, you can take notes, of course, but there is really nothing new. All right? Okay. So this is all the things we've been doing, right? It's been an amazing 14 weeks. Technically 13, because I think there was a Good Friday where we didn't have a lecture, but basically we've been doing quite a lot. It's literally half of the book that we've been doing, the other half being a lot of machine learning stuff. So we've looked into all of these things. Plenty of different ways of building systems, plenty of different ways of modeling the actual data we want to index, a lot of techniques to construct indices in order to accelerate the queries. We have tools to evaluate the system, and we made it all the way, to all the bachelor's level things that I would say bachelor's level is all the way to here, right? Here. And these last few weeks were more challenging, of course, pushing you a bit more to your limits. A lot of formulas. This was more on the master's level, but I hope that it still made a lot of sense to you and that you enjoyed it, right? So there are, as I said in the introduction, 5 fundamental shapes of data: tables, cubes, graph, trees, and text. The other 4 are covered in database lectures. Tables are typically covered in the relational database lectures in the bachelor's level. So it's Professor Chang who gives it for computer science students. Then we have the big data lecture. You're welcome to attend it in fall if you're interested, where we will look at the trees. We also look at tables, but even bigger ones. And normally we even have time to look at cubes and graphs. So we literally cover all of the 4 shapes in the big data lecture. But the text shape is different than the others. It's what we cover in information retrieval, even though I keep saying, and this is why I like to show these slides, information retrieval is really a database lecture. It's a database lecture, except that the data is just text. But this is why we have a lot of techniques that arise from there. So you might remember what we did in the first week. We modeled our input collection as a set of documents, basically a library full of books. And our first query system had this Boolean-based language where you just say the words you want, and you can combine them with and, with or, with not into a query. And then you can execute that query that gives you a subset, because that's either true or false, right? And it gives you a subset of the input documents that you return to the user. What's important to understand is it's a subset. A set is not ordered, and thus there is no ranking. Just that the document is or is not in the output, and that's pretty much it. All right. Okay, so we modeled, we discussed what is a document. So you can typically think of a document as a book, even though we saw that in some cases that might be debated exactly what a document is, like what are the boundaries, how do you divide, and so on. More recently, a document could be a web page, right? All right, we also discussed what a term is. You know, that's always the basis when you build a model. You want to describe the terminology of your model. So we have the document, we have the term. These are the first-class citizens. We also saw that a term is not just about looking at the spaces and taking what's in between, even though, of course, in the first prototype, you typically do that, right? But we saw that it's more complicated than that. You can have spaces like ETH Zurich could be considered a single term. Unterwald and Niddenwald, which is just the longer name for Nidwald. You know, all of these things non-trivially are terms because you might have spaces and so on. And we discussed at length during 2 weeks how complex it is to even say what a term is. But regardless, on the high level, we have our terms, right? So we have a set of terms, we have a set of documents, and then documents contain terms. So this is how we then have the sets of documents, the terms right there, and output them. Then we started abstracting the relationship between documents and terms, and we saw that there are 3 possible models between documents and terms, which are one from the lecture hall, one from Zoom, and then we compete between the 2. Okay, the lecture hall, one of the possible models. Yes? Bag of words, yes. On Zoom, do we have any other possible model?
List of words.
List of words, exactly.
Of words.
And set of, okay, Zoom beats the lecture hall, then we have it before you. So set of words. All right. So yes, bag of words, list of words, set of words. These are the 3 possible models that you can have. What's the difference? Well, it's all about, do you care about the order of the terms in the documents? And do you care about the number of times that the terms occur? These are the 2 things. Set of words means you don't care about any of that. List of words mean you care about both of that. And bag of words means you care about the occurrence, but not about the order. All right? So in the case that we have the set of words, we saw that this is modeled as a vector of Booleans, just ones or zeros. Every position corresponds to a term, right? There's a 1 if the term is in the document, a 0 if it's not, and then we can say that the document is just a vector of Booleans. So this is how we did this abstraction. And so if you want to have the entire collection, then you just put the vectors next to each other, which gives you a matrix, obviously. And we got what's called an incidence matrix. But of course, this is not really great and very space inefficient, as we saw, because there's a lot of zeros in there. And of course, when there's a lot of zeros in computer science, we find better structures. And the structure we found is the standard inverted index, where we have the terms on the left, right here, and they point to the list of documents that contain them. And you see this is semantically equivalent to the set of words model. Do we have questions on Zoom, or is it the previous? I think it's the previous answer, right? Because I see this little number with unread messages. All right. So this is here the standard inverted index. What do we have here? Now you know what it's called, right? What is here? Yes? It's a frequency, yes? Document frequency, exactly. This is the document frequency. It's really just the count. You know, it's just the number of postings we have here. On the chat, I see the also
document frequency.
Yes, we all agree it's the document frequency. Awesome. Yes, indeed. And you saw at the beginning of the lecture, I didn't tell you, I just told you, okay, that's the count. But then we learned later that this is actually called the document frequency. All right. So we have all the terms, the document frequency, and then all the documents in ascending order of ID, because each document has an ID, and they are just sorted by ascending ID. All right. Then we saw that in order to execute a Boolean query, you can just intersect the 2 lists. This can be done efficiently in linear time to compute AND, for example. Then we have the same with the union for OR, and we have tricks for the nodes. All right, we even saw how to optimize the order in which you compute intersection, union, and so on. All right, but this is when you have the index. So we also looked into how to build the index, because building the index might be easy to do with a Python script if it's 100 documents. But if you're indexing 100 million documents, then that cannot be done with just a small Python script, right? In that case, you need some more architecture. So we saw the complexity of all of that, collecting the document, tokenizing, and it's not just about the spaces, linguistic preprocessing, which are a few more tricks that are language dependent, and then we build the index. So we saw that as part of the preprocessing, we like to group the tokens that belong together, right? So for example, if you have be, am, are, is, was, these are all the verb to be, right? So for example, you can group that together. So of course, there's plenty of ways of deciding what you group together and what not, but basically once you group that together, this is called a type. It's an equivalence class of tokens. And once you build the standard inverted index, you stop calling it type, you call it term. So technically, when you say term, you typically mean whatever is there, right? So a term is after the processing, and a token is before the processing. The token is really the raw physical thing you parsed. Type is the equivalence class, and then it becomes a term in the standard inverted index. All right, we saw that for the most frequent terms, we can just drop them. This is what we used to do a few decades ago, because there is just too many documents that have them. We stopped dropping them. We've been no longer dropping them for a few years now, because we have all the computers we need to accommodate for that. So somehow it's out of fashion now to have stop words. But nevertheless, it's important to know what they are and how they are called, because that can be used for optimizations. We saw an asymmetric alternative to the types. So the types is an equivalence class, right? You know what an equivalence class is, right? In discrete math, you probably saw that. It's a relation over two sets that is, and it's like the name of the 7 Bundesrat. I never remember them all, but let me try. It's just 3 here. So an equivalence class is a relation that is symmetric, reflexive, and transitive, right? These are the 3. Yes, I made it. So this is a relation. So it's symmetric, but there is also a non-symmetric way of doing that. That's called query expansion, or depending on which side you do it, query expansion or index expansion. In that case, instead of having equivalence classes, you have pointers from one term to some other terms, but that relation need not be symmetric. And because it's not symmetric, you cannot just do the equivalence classes. You just need to go along the arrows of your relation either one way or the other. So this is just an alternate way that we call query expansion. All right. Then a trick that can be used for, so in that case, it's back to the equivalence class, the symmetric case for the types. One way of building your equivalence classes is to use what is called the Porter stemmer. It's called stemming, where you pick the words and you put them through a pipeline. It's not a machine learning pipeline. It's simpler than that. That is just a set of rules that gives you some unique identifier that gives you the equivalence class, right? So if you take predication, that gives you predicate. Feudalism gives you feudal, differently different, and so on and so on. Yeah, so that's the idea. Don't worry that it's not actually English, because these are the rules, right? So these might be intermediate terms that actually don't make any sense, but it's just part of what you produce in the process. All right, so that's called the Porter stemmer. It's very popular, and you can even download it, and you know, it's pretty cool. It only works in English, sadly, but it gives you a pretty easy way of generating these equivalence classes quite efficiently on English text, and it's right out of the box because you can just download as a library. All right. Then we saw that in the case that we have very short postings lists, and like a very short one and a long one that we try to intersect, that might be quite inefficient because we keep increasing a pointer on the one side and it doesn't move on the other. So we saw that we can have these magical pointers that are called skip lists. In practice, we take the square root. For example, if you have, I don't know, 225 postings in your list, then you will do 15 times 15, right? So 15 is the length of each skip pointer, and you have 15 of them, right? So right. Does it make sense? So these are the skip pointers. These are just helping you to be even faster in the traversal, because then you can just jump ahead for free if you see that on the other side, the other posting list you're comparing to, that you can just directly jump. All right, and then that's the reason we call it a standard inverted index, because it's the standard index, but then there's plenty of variations of that index. Among others, one of the variations is called the byword index. In a byword index, instead of having terms here, we have pairs of terms, help ETH, ETH Zurich, and so on, and you see how we index with a sliding window over here. Apart from that, it's just the standard inverted index. It's just that we have pairs here, and of course, it generalizes to k word indices with any length for the sliding window. Of course, it's not space efficient if k is big, but this is a technique that can work for phrase search. So this is here if you want to be sensitive with the order of the words. And the other possibility for phrase search, so this is by word, the other possibility is positional index. What's the difference with the standard version of the index is that you have the positions of the terms in their original token position in the original document. So you don't have just the ID of the document, you also have all of the positions in the document. So you basically, of course, it's not set of words anymore, right? It's list of words now. But basically, you keep track of the position, and that allows you to see when two words follow each other in a document. All right, so that's called the positional index. And again, for terminology, so these are called terms, right? And these are called positional tokens. Each one of the numbers here is called the positional token because in the same document, it corresponds to several positions of the same term, right? Of the tokens that correspond to the same term. So positional token as opposed to non-positional token, where you don't have the position. All right. Then we saw how to organize the terms in the standard inverted index, because the whole point of the index is that you look up the terms. How do you efficiently look up terms? Well, you've had enough lectures on algorithms and data structures that teach you that. You can use hash tables, and you can use tree structures, right? In databases, we don't just use trees, we specifically use B trees and B plus trees, which database people absolutely love. So this is how you look up, organize and look up terms or any other elements within an ordered set for the trees and not necessarily ordered for the hash tables. All right, this is what a B plus tree looks like. And here, as you're probably aware, if you try to do a Google search or a Bing search or a DuckDuckGo search or whatever on the internet, you probably notice that it's an enormous mess in academia regarding B plus trees because nobody has the same conventions. That's life. I try to stick to the conventions for that lecture, to give you some conventions. In reality, it doesn't really matter. I mean, you learn it one way, you can very easily adapt to any other way of doing it, right? But basically, the convention that we picked is that we give this interval, on the number of either children or keys. Everything here is at the same level. For the B plus trees, the postings are basically also only on the leaves. And here, these are only keys for lookup, but they are not associated with posting lists. This is why they are copies often of the terms right there. All right, and the one thing not to forget is that even though there is this interval of the number of children, d plus 1 to d plus 1 for any value of d, the root is an exception. The root node is the only node that is allowed to have less children than the lower limit, only the root. But of course, it will always have two children, because if the root has only one child, it's just useless to have a root. Then you just remove it and promotes the child to a root. Okay, so this is the B plus tree. Very difficult to implement, which is why we didn't implement it. It's quite technical and has a lot of complexities, but extremely powerful, and any relational database system has something like that inside. All right. We looked into other kinds of queries, so not just Boolean queries and the phrase queries, but also wildcard queries, which is when you have these joker characters in the queries with the star. In that case, it means you look for words that start with food and have a few characters, then ETH, then a few characters, then bar, right? Of course, that's a dummy example, but basically you can have wildcards in your words, and then you need to design the algorithms to deal with that. Somehow, this is not something we typically have in a search engine on the internet, but it's something that you used to have in library search software. You know, in maybe 30 years ago, you go to the library and type a search, then this was actually a thing to try to look up the words. I think the main reason why this disappeared from the popular search engines today is that the popular engines have artificial intelligence technique that figure it out. Basically, if you look for a word, they are able to just use a thesaurus and figure it out even without wildcards. But anyway, so we saw that in order to implement the wildcards, we have yet another kind of index that's called the permuterm index, where when we take each term, we rotate it. So imagine that we put it on a ring and we rotate the ring, and we add this dollar to basically say where it begins and ends. These are all the rotations, right? And then we index to point back to the original term, and that can be used to look up wildcard, some of the wildcard searches, right? Okay, another technique that we saw that we can use is k-grams. K-grams is pretty much the same thing as k-words, right? But then it's about characters and not about words, right? So the k-grams are just sliding windows over the characters within the terms, right? With a dollar at the beginning and a dollar at the ends, and then you can go 1, 2, 3, 4, and so on and so on, right? And you can increase the parameter. There's a lot of places, by the way, in the lecture in which we have parameters like that. We had a parameter for the k-words, we have parameters for k-grams. We had a parameter also for the Markov chains, right, in the language models, where you can also adjust the size of your sliding window, like k-grams it's called. Oh, sorry, now I realize it's the same name. So there's k-grams for the purpose of spell check, and there's k-grams for the purpose of language models, right? So don't be confused that it's called the same, even though you have a sliding window on both sides. All right. Anyway, so this is for wildcard queries and spell check. We have the edit distance that is for spell check. This is to compute, you know, this is dynamic programming. So we compute the distance between two words in this way. This is the typical techniques you learn in also algorithms and data structures. Dynamic programming is just a way of flattening an exponential search space by flattening it to something that is just quadratic or something, and then you can do it in polynomial time. All right. Then we look at the Jaccard coefficient, also used for spell check, which is you take the k-grams of two words, and then you divide the cardinality of the intersection by the cardinality of the union, and that basically tells you how entangled they are, right? So if they are really, really close, the Jaccard coefficient is going to be close to 1. If they are really further apart, it's going to be close to 0, right? So that gives you an idea of the distance between the two, but be careful, it's not a distance, because the distance would be 0 if they are close to each other, not 1, right? So this is why it's not called the Jaccard distance, but the Jaccard coefficient. All right. We also have a Soundex algorithm, which is very nice for comparing how words sound, because maybe people are going to just spell, even native speakers, they are going to misspell something because they just write it the way it sounds. Actually, it's something that could be extremely useful for a language like Swiss German, because, you know, in Swiss German, there is no official spelling, right? Everybody, it's even more today, I think. 20 years ago, it wasn't done that much, but these days, a lot of you probably write Swiss German when you text or write on chat, right? And everybody has a different way of spelling things. So a Soundex algorithm can be very useful for these things, because then you map to some fingerprint of the pronunciation in order to compare the words. Okay, then we looked, in the interest of constructing these indices, we looked at hardware, and in particular storage. And so we saw your computer scientist, so I know you already know all that, but basically you have all these levels with the CPU cache, the working memory, the disk, and the long-term storage with types. You know that without electricity, you still have the data with the disk or a type, but not for the working memory and cache. Okay, you're a computer scientist. I shouldn't even have spent 10 seconds telling you that. You all know that. Okay, we compressed, for the interest of constructing the index, the pairs of document term that we manipulate during the index construction, also called postings. This takes a lot of space. So we compressed it a little bit by replacing the terms with identifiers, term IDs, right? So then it takes less space into memory, and so this is what we did here, right? So it's just a way of encoding. It's also called the dictionary encoding in the database world when you use IDs instead of values that repeat. Okay, and so based on that, we defined one possible way of building the standard inverted index, which is called BSBI, blocked source-based indexing. And the idea is that we can process even collections that are bigger than the disk, right? It's pretty impressive because you would think, okay, if it's bigger than the disk, we cannot process that. But in fact, yes, we can. In two ways. The small way is it's bigger than the memory, but it fits on the disk. Then you can do it with a single machine. If it's bigger than a disk, then you need a cluster. So we first look at a technique that fits on one single machine, but not in the memory. And in that case, we shard the input into different partitions, and we process one partition at a time, but every partition is going to fit in memory, right? And then we produce this term IDs document IDs pair, and then at the end we have this merge that is similar to the second part of a merge sort, where we just in linear time can merge two sorted lists. All right, so this is the first one. Then there is an improvement that came later that's called SPIMI, single pass in-memory indexing. That is pretty much the same thing, but a bit more modern. They basically made it a bit more efficient. You don't need term IDs anymore. Then you directly produce intermediate standard inverted index, but they are just partial. They only index the shard or the partition that you are processing. And then at the end, you can merge them again in linear time. And finally, if it doesn't fit on the disk, then you can go to a cluster of machines. This is the kind of things we actually do in the big data lecture. So maybe next fall, if you are interested. But basically, we can use a technique called MapReduce in order to process massive amounts of documents. And with this nice algorithm, we manage to shuffle data around in the cluster and magically produce the final standard inverted index. All right, logarithmic merging is the technique that is used, you might remember, in the context of collections that change over time. So it's not like you have a static collection that never ever changes. It's like the internet, the web. There's new web pages that get created all over the time, that get refreshed and so on. So how do you deal with it? And we saw there's plenty of ways. And one of the ways is to have periodic updates to your index, but you structure them in exponentially growing file sizes, right? And that's called the logarithmic merging, or LSM tree is also called. And the idea is that you just always create new files that have a fixed size, but whenever you have several of them, you merge them into a file that is twice as big, and you just keep pushing and pushing and pushing to more and more files. But since you double every time, it's very efficient. And I think it is in this lecture, I can't remember if it is in this lecture, in the Big Data for Engineers lecture, that one of you mentioned, it's like the 2048 game. You know the 2048 game, right? This is pretty much what it is. You're basically playing 2048 with the files in there. This here is also a big data technique, something that is used in some of the large-scale big data systems for large databases that you want to update efficiently, like HBase, Hadoop, HBase. All right, so that's also something, if you want to come back in fall, that we'll study more in depth. Okay, then we did a bit of statistics. We looked into the distribution of the number of tokens when you have more and more and more and more documents. More precisely, the number of unique tokens. So basically it says, if your collection grows, how does the height of your index grow? And we saw it's pretty much in the square root, right? So if the collection grows by a factor of 100, then the number of terms or of tokens, it's kind of all equivalent, right? Because it's statistics on the large scales. But basically the height is going to be times 10, right? If you multiply by 10,000 the size of the collection, it's times 100 for the height of the index. So this is called Heap's law. It's purely observational. We just looked at real data, and this is what we found. Right? Heap's law is another one that is also completely experimental. It's just based on observation. Is that if we look at the term frequencies, the the frequencies of the terms in. So I should say the collection frequency, I think, would be the accurate name. So how many times does a term occur in the collection is going to be distributed hyperbolically, 1 over x. Right. So basically, the first one is going to be, if it's 1, then the second one is 1/2, then 1/3, 1/4, and so on and so on. And it's just going to distribute that way. So here you're going to have the stop words like V, A, is, B, and so on. And here you're going to have the super rare words that nobody ever understands, you know, that are very rare in your collection. All right, so 1 over x, and that's called Zipf's law. So Zipf's law square root, Zipf's law 1 over x. Okay, and given these laws, that actually drove the entire field of index compression. So we saw how we can compress the standard inverted index to make fit even more data into less space. So we tried to encode the terms, and then we tried to encode the postings list. So to compress the terms, one of the ways to do that is called front coding, when you share a prefix of several terms that start in the same way, and you can save some space by not repeating that common prefix. And when you do that, then you can have pointers only every k terms, and then you save space with the pointers, right? So these are just tricks in order to try to squeeze more into less space. Okay, what else did we have? Well, we also tried to encode the postings, which are the document IDs on the right of the standard inverted index. We saw that one of the ways to compress is called variable byte encoding, right? Why did I call it variable byte encoding? No, sorry, it is. For a moment, I thought that was the gamma code. No, that is the variable byte encoding. You can see because there's packets of 4. So 4 and then 8 and so on. So these are packets of 4. So it's variable byte encoding. You see that at first you use a single packet of 4 bits, and then you switch to 2 packets of 4 bits and so on and so on. And the first bit of each packet tells you whether or not it's the final packet, right? So the 0 tells you that it's the final packet, and the 1 that it's not the final packet, knowing that it's a convention thing. So you might also see it the other way around. Okay, so this is the variable byte encoding. And you see at 64, we switch to 3 packets. Note that the size of the packets is a parameter. Here it's 4, but you can use 8, you can use 16, you know, it also works. It's all a matter of compromise. Okay, and then the all-powerful and absolutely awesome gamma encoding that is just completely elastic, that just shrinks to just 1 bit if you encode 1, and that elastically grows as the numbers get higher. And the way it's done is incredibly simple. You just convert it to base 2, drop the 1, the leading one, and replace it with a mirrored version of the right with 1, 1, 1, 1, 1, 1, 1, but as many bits as there are bits here, right? So it's almost symmetric there. And that's the gamma encoding. So as you observed in a question, it's always an odd number of bits for that reason. You always have the 0 in the center, 1's on the left, and then all of the bits of the binary version except the leading one. Okay, so that is the gamma encoding. Okay, so this is index compression. Then we tried to rank the documents that we have in our system. So we slightly modified the system by saying, okay, now we have a query. It might not be a Boolean query. It's more the queries you type in a search engine or the web. And then you return that in the web search style where you have the top 10 documents. Then you click next, you have the next 10 and so on. So we rank the documents and display the ones with the highest score to the user. So we need a concept of score, computing a score for every document. And then we spent several weeks doing ranking in plenty of ways. One of the trivial ways, well, almost trivial because it's been solved 50 years ago, is in the case of a good old relational database where you have metadata on your books, like the title, the author, the language, the country, and so on. You can just turn that in a database problem, and then you can very easily compute a score by the number of fields that actually match. Right. So this, we just quickly discussed it because this is really about turning that into a database problem where we build database indices on the fields using B+ trees hash tables, right? So then that gives you something hybrid, is that for some of the fields you have a totally classical database index, and for some other of the field you create a full text search with the standard inverted index. All right, but we didn't spend much time on that because there is not much interesting to say about that. It's just about mixing it together. The really interesting part started when we introduced the linear algebra in the picture. So in order to build the vectors that we need for the linear algebra approach, the vector space model, what we did is that we computed the term frequencies. So a term frequency needs a document and a term. So if the documents are here, the terms are there. And the term frequency of document A for term foo is 5, meaning there's 5 times foo in document A. So it's a bag of word semantics where we know the occurrence. On the other hand, we have the IDF, which is the inverted document frequency, the logarithm of the total number of documents divided by the document frequency. That gives us an indication of how rare a term is. And the magic weight, or the magic technique, is called TF-IDF. So something you have to know by heart, TF-IDF, which is the product of terms frequency times inverted document frequency. It is probably the one most popular weighting scheme in the vector space model. If you don't know what to use, just use the TF-IDF. That's the default. Then, of course, you can tweak it and use other techniques, but TF-IDF is really the default. And you just multiply this with that and get the weights, and then you recognize like this is the vector for document A, this is the vector for document B, and so on. So this is just, again, as I said, we have now vectors, not vectors of Booleans, but vectors of numbers, because we are in the bag of word semantics. And when we do that with vectors of numbers, they are positive. So we are basically the first quadrants of a vector space of a certain dimension. The dimension is the number of terms, which we call M. So this is it. Every document is a point in some vector space. And what that means is that the queries also are points in there, because the queries can be seen as documents. And we can just measure the angle that separates a query from a document in order to score the documents. So in order to measure the angle, we can use the cosine of the angle, and you might know the cosine is obtained with the dot product, because you told me this is how you call it. So we do the dot product of 2 points in that vector space, a query and a document, for example, and the dot product is going to be a proxy for the angle between the two. The closer to 0, the higher the score of the document. Sorry, the closer to 1, the higher the score of the document, right? If you renormalize everything. If it's 0, it's orthogonal. The dot product is 0 if there is a right angle. Okay, so that's the secret, a sum of products, the dot product. And it turns out that the dot product is super easy to compute and to scale with something we call evidence accumulation. And it turns out we can just use the variation of the standard inverted index, and we can just traverse like this and like that and accumulate all of this part of the dot product. We accumulate that part into these buckets, one per document, and then we keep summing. So this is the sum part. And at the end, we have the scores for all the documents that are actually the dot products of the document with the query. That is the secret on the very high level. And it works not only with TF-IDF, but with pretty much any scheme that you choose to use, right? And in order to decide which scheme to use, we have this restaurant menu coming from a system called SMART that is several decades old. And now what people remember of that system is pretty much this scheme. It was bigger than that. Of course, it was a real complete system. But again, this notation for picking the weights is what people remember. Okay. And then came the master's level of the lecture. It turns out to still be something that is done with the vector space model and evidence accumulation and dot products and so on. But this time, instead of the TF-IDF, we use a weighting scheme that is derived from considerations on probabilities, and more exactly on Bayesian probabilities. So we had a thought experiment where we try to rank the documents. So in that case, I have F, D, F, E, G. And I'm ranking them that the probability that they are relevant to the query queue. So what we did is that we spent 2 hours torturing an equation in order to turn it into something we can compute. So I'm sparing that to you today and directly showing you the final results that after a lot of simplifying assumptions we came at. And it turns out that we got back something that incredibly resembled the inverted document frequency. And that is a beautiful justification for actually having used the TF-IDF, or at least the IDF part in our formula, right? So this is what we got out of the probabilistic information retrieval. And then in the lecture after that, so that was last week, then we looked at something different that's called language models. And the language models are how you can consume plenty of documents by an author and then revert the engine to produce new documents that seem to be from the same author, right? So these are the language models. And we saw that the way it works is with these chain rules of probabilities, where the probability that we obtain a specific document is just the probability that it doesn't stop, and then we get this term, and it doesn't stop, and we get this term, and it doesn't stop, and we get this term, and it doesn't stop, and we get this term, and it stops, right? So it's just, again, a chain of events in there. And we saw that thanks to the Markov rule, we don't have the entire past in there, but we have a limited memory. We only remember what happened in the past 2 days. And so we drop everything that's earlier than that, and that gives us Markov chains. All right, so basically what this gives us is the probability of generating a specific document with a model with this formula right there that we studied. And then we had this beautiful thought experiment of saying, if I have a query and I, in my imagination, woke up to the ETH library 1 trillion times, and every time I pick a book, I build a model and I generate something, and I do it 1 trillion times, and then I look at all the times that I generated the query right there. So if I do it 1 trillion times, then maybe 3 or 4 times I'm going to have the query. And then I use Bayesian analytics or Bayesian formulas to try to find the document that is the most likely to have been used to generate the query. So it looks a bit circumvoluted in the way of the thought is done, but it's actually beautiful because it gives us yet another way of scoring the documents using Bayesian reasoning. So it is what the score of a document is the probability that it happens to generate the query out of a model based on the document. And here, the one thing that is absolutely beautiful is just like we got the IDFs from the probabilistic information retrieval, we got the term frequencies from the language models, right? And the way you get them is that they are in the product, right? So we saw, you remember, was last week, this is a constant that we drop. This is a constant that we drop. So there's only that. So now you're going to tell me, yes, 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 but this is a product, not a sum. Yes, but you know that we're computer scientists. We know how to turn products into sum. We just take the log. So if you take the log of that, you basically get the sum of the logs of the term frequencies. So then, of course, that's not exactly the term frequency. It's the log of the term frequency. But it turns out that's on the smart menu, right? On the smart menu, you also have the log version. And if you've been wondering why the log version, because of that, because of the language models that actually justifies using term frequencies and in particular using the log. Okay, then we looked into the evaluation of systems. Oh, it's about to ring, so I maybe a few more slides. We saw precision, recall, specificity, the F measure, which is trying to weight between precision and recall. We looked at precision recall curves when we have ranked retrieval to see how the precision decreases when you go down the results. And the ROC curve, that's just another way of doing that, actually inherited from electronic devices. And again, this is used in machine learning a lot. Right? So it's basically if you turn the knob of your metal detector, how sensitive is going to become, and then start beeping too much, right? And you want the curve to be as much as possible on the top left if you have a good system. All right. It's probably going to ring the bell now, so I'm going to tell you about the exam right after the break, and we'll have our quiz, right? That's, as you can see, that's the last slide, and we'll practice for the exam. So I'll see you in 15 minutes for a few words on the exam and the quiz game. And yeah, we'll have fun at the end of the semester. So thank you and see you in 15 minutes.